Welcome. This is a lecture about partial fractions, which is a technique in calculus. Um, the idea is, how do you do something like the integral of 1 over x squared plus 1? Well, we all know what that is. That's tan inverse. But what if I gave you the integral of 1 over x squared minus 1? You could try and make some clever substitutions and mess around, but you're probably not going to get it. And the reason is there's a crucial point, which is that x squared minus 1 factors, unlike x squared plus 1. X squared minus 1 factors by difference of squares. And it turns out that this 1 over the product of these two terms can be rewritten as the sum of two terms, each of which just has a linear factor in the denominator. So this is the key step in partial fractions. You rewrite something with a product in the denominator as a sum of terms. And so let's just check, why is this true? If you take 1/2 over x minus 1 and you multiply it by x plus 1 over x plus 1, and then the other term you multiply by x minus 1 over x minus 1 to get a common denominator, what happens is the denominator is exactly what you started with, x squared minus 1. And the numerator is what? Let's see, 1/2 x minus 1/2 x plus 1/2 plus 1/2 is 1. And so the key step in partial fractions, well, partial fractions is just algebra. And that's one nice thing about it. It's straightforward, and at the end of the day, you wind up with an integral that you can do. But the key step is the algebra to get there. So the last step in doing one of these is you get this integral, and on the right-hand side, the integral is easy. It's 1/2 log absolute x minus 1 minus 1/2 log absolute x plus 1 plus c. Okay, so the basic idea behind partial fractions is the following thing. You're given an integral of a ratio of two polynomials, and what you do is you replace this integral with a sum of terms, each of which is a similar ratio of polynomials but of smaller degree. And the point is that these integrals on the right you're supposed to be able to do. They're things which are simple, and you get things like logs and arctangents and so on. So that's a little vague, but that's the outline. You do some algebra to replace a ratio of polynomials with a sum of simpler ratios of polynomials. Okay, so I'm just going to illustrate that now with a bunch of examples illustrating the main points. So here's a very simple example to start with. What if you had x over x plus 1? Well, what are the degrees here? So in the numerator, it's x to the 1, and in the denominator, it's x to the 1. So the numerator and denominator have the same degree. And when that happens, you should do long division of polynomials, because that will make it easier. So let's see how that works in this example. You divide x plus 1 into x. Well, you think of x as x plus 0, and you put a 1 here, and here you put x plus 1, and you subtract it, and you're done. It says that x over x plus 1 is equal to 1, this thing up on the top here, and then plus a remainder, which is minus 1, over x plus 1. So that's just an algebraic identity. And let's just check once again, is that really right? X plus 1 over x plus 1 over x plus 1 plus minus 1 over x plus 1 is indeed x over x plus 1. You get a common denominator. And so the integral is now easy to do. You just get the integral of dx plus minus the integral of 1 over x plus 1, and that's simply x minus log absolute x plus 1 plus c. So the general principle here is that if you're given an integral of the ratio of two polynomials, you look at the degree in the numerator and the denominator, and if a is bigger than or equal to b, I should have said bigger than or equal to, then you do long division and you replace it with a simpler problem. Okay, so let's do another example. Suppose I gave you the integral of 5x over, let's do x squared plus x minus 6. So the degree in the numerator is 1, and the degree in the denominator is 2, and 1 is less than 2, so you don't need to do this first basic reduction step. And now when the key question when you have something like this is whether the denominator factors. Like in the very first example, x squared plus 1 doesn't, but x squared minus 1 does, which gives very different answers. So let's check, does x squared plus x minus 6 factor? Well, yeah, it does. It's x minus 2 times x plus 3. And so the main step in partial fractions for this guy is you write 5x over x squared plus x minus 6. You first factor the denominator, and then you try and write that as something, a constant, over x minus 2 plus some other constant over x plus 3. I wrote minus 3 there. That's a misprint, should be plus 3. And you try and find a and b which make this true. And if you can, then you've got an integral that you can do. All right, well, so let's see. Let's write 5x over this thing as a over x minus 2 plus b over x plus 3. And, well, you just have to figure out what a and b are, and the way you do that is you get a common denominator on the right by multiplying the first term by x plus 3 over x plus 3, and the second term by x minus 2 over x minus 2, which is the same thing as cross multiplying. And you, in the numerator, you get this term, and the denominator gives you this x minus 2 times x plus 3 that you started with. So for these two things to be equal, these things circled in blue have to be equal, which is to say 5x has to equal ax plus 3 plus bx minus 2. And that says that 5x is equal to ax, a plus b times x, plus 3a minus 2, grouping things, 2b, grouping things by the power of x. And this is the equality of two polynomials in x. It has to be true for all x, and the only way that can be is if the coefficients of x agree, which is to say 5 is equal to a plus b. And on the other hand, the constant term on the left-hand side, which is 0, has to equal 3a minus 2b. So this is a pair of equations to solve for a and b. If you multiply the first one by 2 and add it to the second one, the b's cancel, and you conclude that a is equal to 2, and from the first equation that b is equal to 3. So it is possible to rewrite this guy as something where the terms in the denominator are linear, and then that makes it possible to do the integral. All right, I'm not going to do the integral, but it's a sum of two log terms. But let's go on and do another example. Suppose I gave you x minus 1 over x squared plus x plus 1. Well, again, the degree in the numerator is less than the degree in the denominator. So you ask yourself, can I factor the denominator? And, well, the sort of authoritative way is to use the quadratic formula, and you see that the roots of this polynomial are minus 1 plus or minus the square root of minus 3 over 2. And remember that you can factor this thing only if these two roots are real, and in this case the square root of minus 3 messes you up, and the answer is no, you can't factor this thing, not over the reals. So when that happens, instead you complete the square, and you write x squared plus x plus 1 is equal to x plus something squared, and the something you put in here is 1/2, because that gives you x squared plus x plus a fourth, and then you have to add a 3/4 to it, so this comes out to be x squared plus x plus 1, and that completes the square, and you replace the integral with the integral of x over this thing minus 1 over this thing. And after change of variables, you should be able to do both of these terms, both of these integrals. So let's see how that works. So the first term, you're going to let u be x plus a half. Well, actually in both terms, so that du is equal to dx, and x is equal to u minus a half. So the first term becomes u minus a half over this thing, u squared plus 3/4 minus 1 over u squared plus 3/4 du. And let's see, well, let's bring this constant term over to the other side. So this becomes u over u squared plus 3/4 minus the integral of, let's see, 1 plus a half is 3/2, and so it's minus 3/2 u squared plus 3/4. And we know how to do both of these integrals. The first one, you make another substitution. W is equal to u squared plus 3/4. dw is equal to 2u du. And this becomes the integral of, let's see, u is 1/2 dw over w, which is 1/2 log absolute value of w, and that's 1/2 log, let's see, w is u squared plus 3/4, and u squared plus 3/4 is x squared plus x plus 1. So that's the first integral. And the second integral is, that's an arctan. What do you get? You get 3/2 times tan inverse. Let's see, it's u over radical 3/4, which is to say minus 3/2 tan inverse 2u over, 2x plus 1 over radical 3. Okay, so that's the second integral. And again, the integration part isn't the key thing here. It's getting to the point where you can integrate it, which is the heart of it. Don't forget your plus c. And so that's that integral. Okay, let's look at another example. How about, what if I asked you to integrate x over x plus 1 squared times x minus 2? Well, the bottom's already factored, so let's see if we can write x over x plus 1 squared as something over x plus 1 squared plus another constant over x minus 2, and try and find a and b. Well, let's see. So the right-hand side, when you get a common denominator, is a x plus 2 plus b x plus 1 squared, a x minus 2, excuse me. And this numerator had better equal x. And so that is, you have to solve x is equal to, let's see, ax minus 2 plus bx plus 1 squared, which is ax minus 2a plus bx squared plus 2bx plus b, and you square the second term out. And if you group terms, this is, let's see, bx squared plus a plus 2bx plus minus 2a plus b. And you're trying to figure out what a and b are. Well, let's see, b has to be 0 because that's the x squared term. And if b is equal to 0, let's see, that says that a has to equal 1 from this second term here, because this is supposed to equal x. So you conclude that a has to equal 1. And let's see, this last term turns out to be, well, you know that A is 1 and B is 0. This comes out to be minus 2. And that's a bummer. That's too bad, because that was supposed to come out to be 0. And it didn't. And I have no flexibility left. A and B were forced on me. And so I lose. This didn't work. So when this happens, what you say to yourself is, well, I must not have given myself a general enough term in the beginning, this thing with the A and the B. And you need another term somehow. And the idea is that this A over x plus 1 squared, well, the fact that the x plus 1 is squared suggests that maybe you should also have a term which is something over x plus 1 to the first. Let's call that C. And that's what works. So let's see how that goes. So I was illustrating it this way to show you that if you try and solve one of these problems and you can't, you know that you need a more general term. So let's write this as a over x plus 1 squared plus b over x plus 1 plus c over x minus 2. I changed b and c here, but that's fine. And now the right-hand side is going to be a times x minus 2 plus b times x plus 1 times x minus 2 plus c times x plus 1 squared over the denominator. And this had better equal x. So you're trying to solve x. Let's see, we're trying to solve x is equal to this thing in the numerator. Well, let's multiply out the numerator. You get b, let's see, x squared minus x minus 2, and then cx squared plus, sorry, that last term is not right. It's c x squared plus 2cx plus c, and that's all supposed to equal x. And so let's just look at the, let's see, here's the x squared term, so we'd better have that b plus c is equal to 0. And here are the x terms, there are 3 terms, so we'd better have that a minus b plus 2c is equal to 0. Excuse me, 1, that's the x term. And then finally the constant term is minus 2a minus 2b plus c. And that had better equal 0. So now I have 3 equations and 3 unknowns, and I have a chance at solving it. And, well, I'm not going to go through the painful process of solving this. It turns out that it gives a is equal to 1/3, b is equal to 2/9, and b is equal to minus 2/9, and c is equal to 2/9. And you can easily check that that is the correct values of a, b, and c. And so then you get an integral that you can do. And here's the answer. At the end of the day, you get logs and various things with these coefficients. But of course, again, the key point for the partial fraction step is just finding this a, b, and c. Okay, here's another polynomial problem with this cubic polynomial. And when you have a cubic, you need to try and guess a root. So let's see, if you plug in 1, you get minus 2. That's too bad. Let's try 2. You get it, let's see, 8 minus 8 plus 2 minus 2 is equal to 0. Good. So 2 is a root, so that means that this thing can be factored, where one of the factors is x minus 2. And the other is going to be quadratic, something with a squared term. And let's see, how do you figure that out? Well, you do long division. X minus 2 into this thing looks like what? Well, the first term is x squared, which gives you x cubed, minus 2x squared, and that's 0. And then you get plus x, and that gives you 1, and minus 2 is equal to 0. So the answer over here is x squared plus 1. Okay, so that's the first step, is just factoring the denominator into linear and quadratic terms. And so now, let's see, how do we do this integral? X squared plus 1, x minus 2, excuse me. Let's see, well, let's try and make this equal to a over x squared plus 1 plus b over x minus 2. And, well, it turns out that this x squared term suggests that that's not good enough. What you need is ax plus b over c x minus 2. That's just the way these things work. And so let's try and work this out. When you get a common denominator, you get this. And when you multiply it out, you get ax squared, let's see, plus b minus 2ax minus 2b plus cx squared plus c. And that is to say, the coefficient of x squared is a plus c. And the coefficient of x is, let's see, b minus 2a. And the constant term is minus 2b plus c. And we set these equal to 0, 0, and 1, respectively. And we try and solve. Well, let's see. That says that c is equal to minus a, b is equal to 2a. And then this last thing says that minus 4a plus minus a is equal to 1, which is to say a is equal to minus a fifth. Okay, so I'll write it up here. At the end of the day, it turns out that a is equal to minus a fifth, and that gives that b is equal to minus 2/5, and that c is equal to 1/5. And when you plug those in, you get an integral that you can do. And I'm not going to actually do it, but I'll stop there.